In this video, we're going to talk about a new continuous distribution. So we are adding from the continuous uniform distribution and to the normal distribution something called the exponential distribution. The exponential distribution. And it is what it sounds like. It involves an exponential curve. In fact, if you wanted to take a quick sketch of what you might think this looks like, that would be correct, in that it is going to take on this shape right here. If that would be your curve there, that would be an exponential distribution. Remembering the probability being represented as the area under the curve here, this is sort of saying that the likelihood of the lifetime of something or your random variable x going further on this line here, it gets lower and lower and lower, as in the sense that the area under the curve, for example, from this point to this point is a lot less than the area under the curve from, these 2 points right here. And so most of the probability density is weighted towards the front, but it does have a long tail that goes on indefinitely. Let's write the definition down then. The continuous, this is obviously continuous, the continuous random variable x has an exponential distribution. And with an exponential distribution, you have one parameter with scale parameter beta if its p.d.f is given by the following: f of x, one scale parameter beta, is equal to 1 over beta e to the negative x over beta. And this is good for all x greater than 0. All x greater than 0. And so the typical exponential curve looks like what we have sketched in that graph. A couple of things to be aware of here. Notice that certainly this is not symmetric like the normal distribution is, right? So first comment, just be aware. Note this is not symmetric. Very much not symmetric. All right. And there are a couple of nice things about the exponential distribution that are sort of worth remembering. And that is that the expected value of the exponential distribution is equal to beta. And the variance of an exponential random variable is your scale parameter squared, is beta squared. That is your variance, is beta squared. So I guess you could also sort of say the standard deviation is beta as well. So the expected value and the standard deviation are the same. That is the scale parameter beta here in regards to your exponential distribution. And beta usually would lie along somewhere around here, although we can take a look online or take a look in the book for some more computer-generated images as far as how changing beta affects your graph. But that is the exponential distribution. It's an exponential curve, exponential decay curve, and the expected value is beta. The variance is beta squared. Let's take a look at an example here. The life in years of a type of electrical switch has an exponential distribution with an average life of 2. What is the probability a given switch fails during the first year? This is a very typical type of exponential distribution question, talking about the lifetime of something. So there's this sort of theoretical potential that the switch never breaks. But it's the longer the switch is lasting, it's unlikely that it continues to last longer. And an exponential decay curve is really good at modeling that. So this is a very typical type of question here. And in order to get some of these probabilities, we are actually going to have to use some integration. We're going to have to integrate our exponential curve. And so, excuse me. something to think about real quick, if we haven't done this in a while, remembering the antiderivative of something like, e to the kx dx, knowing what that basic antiderivative would be. And this is e to the kx divided by that coefficient k plus c, if it's an indefinite antiderivative. And in this case, this is similar to what we have here, except we have e to the negative x over beta. Beta is a constant, and so we might want to prep ourselves by just thinking about, well, what would the antiderivative of e to the x over k be? Well, then you would have e to the x over k, and you would be dividing by 1 over k. Dividing by 1 over k is the same thing as multiplying by k. So ke to the x over k would be our antiderivative. And we can use that sort of thought process as some prep for doing this type of question. The life in years, it has an average life of 2 following an exponential distribution, an average life of 2. So that means we know that beta is equal to 2 here. Beta is equal to 2. So our distribution is f of x, exponential distribution with a scale parameter of 2. So that is going to be 1 over beta, which is 1/2, e to the negative x over 2. And this is good for x greater than 0. So what is the probability the given switch fails during the first year? That would be the probability then that x is less than 1. Fails during the first year, an average life of 2. I suppose that kind of goes without saying that there's an average life of 2 years here. This is assumed to be an average life of 2 years. And so failing during the first year, we want the probability that x is less than 1. And so how do we get that area under the curve? We want to integrate 1/2 e to the negative x over 2 dx. Integrate your p.d.f. X less than 1, you have an upper bound of 1 and a lower bound of 0 because, again, x is defined to have to be greater than 0. So we integrate from 0 to 1 there. 1/2 e to the negative x over 2 dx. And that is the correct setup. So first step will be getting our setup there. And so now we need to do the antiderivative. We have a constant factor of 1/2 I can bring out front. And then we just need to integrate e to the negative x over 2 dx using the calculus skill that we had above there in green. So I've got 1/2 constant multiple in front. Now I take the integral. Here. I'm going to have 1/2 times, let's see here, the antiderivative, like we have above here, is k. So this is going to be 2 e to the negative x over 2, evaluated from 0 to 1. And I'm missing one thing here very carefully if you check your calculus. So I'm applying this rule right here. And I'm missing one specific detail. What we're missing is, don't forget this negative sign right here should come down with that as well. And so let's take a look at what we have now. The 1/2 and the 2 cancel. This is something that's going to happen commonly with the exponential distribution. And we have the negative sign out in front, so this is equal just to negative e to the minus x over 2, and you plug in and evaluate from 0 to 1. If you're like me, you like to absorb the negative symbol in your integration bound, so I'll just take positive e to the minus x over 2 and switch my bounds from 1 to 0. And so now we evaluate this, e to the 0 minus e to the negative 1/2. This is 1 minus e to the negative 1/2. That is an exact answer. If you want to round this to 4 decimal places for a probability, it's about 0.3935. Typical exponential distribution question there. Let's do one more example, and let's continue this problem. Continued. if 100 of these switches are installed in different systems, what is the probability that at most 30 fail during the first year? What is the probability that at most 30 fail during the first year? Think about what we just answered above. We know the probability that a single switch fails during the first year, but now we're essentially looking at 100 of these. This is like one of those binomial random variable inception type questions that we encountered quite a few weeks ago. So I'm going to go ahead and define y here to be a new random variable that is counting the number of switches that fail in the first year. So y then is binomial. It's a binomial random variable. I'm just using y instead of x because I've already used x in the previous part of the problem here above. You're doing n equals 100 trials. 100 of these switches. And what is the probability, your success probability, quote unquote? I'm doing air quotes here. I know no one can see me. The success probability that a specific switch fails during the first year then is 0.03935. That is the number that we got above right there. And we want the probability that at most 30 fail during the first year. And so we want the probability that y is less than or equal to 30. We want the probability that y is less than or equal to 30. Well, this is the cumulative distribution probability, and as we just looked in the last video, we mentioned the binomial random variable, the p.d.f table in the back of the book, only goes up to 20 trials. Only goes up to 20 trials. But you're saying, well, hey, aren't we talking about exponential distribution questions? Well, yes, but we've already done the exponential distribution part. This question is just about a binomial random variable. And so we're going to utilize what we had just looked at in the previous video, and let's go ahead and check for a normal approximation. Is this a good question to use a normal approximation on a binomial random variable? N times p here, 100 times 0.3935. We run that through a calculator. That is 39.35. Is that large enough for a normal approximation? Well, we go back and look at our notes. A normal approximation to a binomial random variable is good if np and n times 1 minus p are both greater than or equal to 5. That's certainly greater than or equal to 5. In fact, this is going to be the mean mu in your normal approximation. And let's just finish checking n times 1 minus p. We can plug that in and run that through a calculator. That actually ends up being 60.65. And so this is certainly large enough of a size to do a normal approximation. We have the mean of 39.35. Sigma squared then, you look back at your notes for that last one, that is going to be np times q, 39.35 times 1 minus p, so that'll be times 0.6065. And we should get sigma squared then. Well, I'm just going to leave it like that for now. That would be my sigma squared. Right, sigma squared is np times 1 minus p. And so if we want the probability that y is less than or equal to 30, this is approximately the same thing as a standard normal question. We have z less than or equal to 30 minus the mean here, which is 39.35, plus the continuity correction, divided by the standard deviation, which would be the square root of this product, 39.35 times 0.6065. And so we need the probability that a standard normal random variable z is less than or equal to negative 1.81. And we can look that up in the table. That's about 0.0352. 0.0352. So I like this example because I do want you to see that in all sorts of these distributions, a lot of times we can get questions after the fact that end up being binomial random variables. We've seen this before in even the discrete chapter that we had done. We've seen this in a normal direct relation to the normal distribution as well. And so in this question, the first part of the example is really the new introduction to the exponential distribution. So make sure if you have questions, ask those below in the discussion. But that's not, it's not too much. We're not going to worry too much about the exponential distribution, so we're not going to spend a lot of time there. If you are looking in the book, this section also does include the gamma distribution, and we are not going to worry about that for now, given our circumstances. We're just going to focus a little bit on the exponential distribution. So not a lot of effort there in some sense compared to the normal distribution, but it is something we do want to be aware of as well.